Good afternoon, everyone. I'm Tony B. My co-authors for this presentation is Dr. Hao-Chi Wan and Dr. Roland Clift. The title of my presentation is The Optimal Use of Waste Biomass for Meeting 2030 Paris Target. As everyone here knows, the potential for decarbonization for electrical vehicles will depend on where the electricity is generated, either from the fossil sources or from the renewable energy sources. Similarly, if we want to ask what is the waste biomass potential for decarbonization, it will depend on how the waste biomass is utilized, either for the heating, for the biofuels generation, or for electricity or the biohydrogen production. As well, it will depend on what kind of the fossil fuels it will be displaced. This will be strongly dependent on the energy structure of specific countries or specific regions. So there's no single answer for any country or any region. So we carried out a case study for the British Columbia, a province in Canada. So for this specific region, we examined to meet the 2030 reduction target, what kind of the energy demand will be predicted based on kind of the energy transition analysis. Then we look into what are the energy supply needed to meet our demand and then to meet the target. It is showing that at least 20% additional electricity needed produced, or we will have a shortage of 20% of electricity by 2030. Similarly, for the bioenergy, that is another renewable energy source, we will have a 20% of the shortage of the biofuels, which need to be either imported or produced from other kind of the arrangement. Clearly, another strategy will be how to optimize the electricity use and the biomass use so that we can increase the potential of decarbonization using the existing supplies of the electricity and the biomass energy. So the objective of this analysis is how to maximize the biomass waste use for the greenhouse gas emission reduction. So first, we look into the different biomass utilization pathways to see how we can optimize the GHG reduction. So as everyone knows, the biomass can be used for the combustion or methanol production, bioethanol production, renewable natural gas production, or the biogasoline, biodiesel, or biojet fuels production. Then it will displace different type of the fossil fuels. Again, our analysis is based on British Columbia in Canada. So we quantify our result based on per dry ton of the biomass, how much of the CO2 can be reduced. As shown in this diagram, the direct heating of the biomass will achieve the highest CO2 reduction potential, followed by the liquid biofuels like the biogasoline and the biodiesel, biomethanol, bioethanol, and then renewable natural gas and the combined heat power generation. The least reduction potential is the biomass for the power generation. This is because we have a relatively clean electricity mix in British Columbia. In terms of the costs, we quantified per gigajoule of the energy, how much it will be costs. Again, as shown in this diagram, the biogasoline, biodiesel production, biomethanol, bioethanol, and then the renewable natural gas will have all the higher costs compared to the counterpart of the fossil fuels. Particularly for the renewable natural gas, because of the very, very low natural gas price in North America, the cost of the renewable natural gas is the multiple times of the natural gas. The power generation from the biomass also will have the high cost than the power generation from the other sources in British Columbia now. The only comparable bioenergy use is the direct heating or combined heat and power, which is comparable to the natural gas heating and the electricity generation in the province of British Columbia. Based on this analysis, what our recommendations are, we should focus on bioenergy deployment for the industrial district and the district heating, replacing the natural gas. This will be the strategy for meeting our 2030 target. For the strategy to meet the 2050 carbon neutral target, the biomass should be converted to the liquid biofuels to decarbonize the long distance transportation, because in the near future, we do not see the electrification can be applied to this long distance transportation. Next, we examine is how to integrate our energy systems to maximize the bioenergy potential for decarbonization. So we take a case study looking into the anaerobic digestion, a very, very promising technology to convert the high water content organic waste into the biofuels, including the food waste, animal waste, industrial, and the municipal sludge. In the anaerobic digestion, all this waste will be converted to the biomass, but not to the biogas. The biogas will be upgraded to the renewable natural gas or combusted for the heat power generation. And then the digestate can be land spreaded or upgraded to the compost as the organic fertilizer. As we discussed before, the combustion of the biogas for the power generation will lead to very, very small GHG reduction because of the clean electricity mix in British Columbia. While the renewable natural gas will be economically not comparable to the low price natural gas in North America. The most promising application of the biogas will be for the heat generation. However, because most of these animal farming operations is located in the remote areas, we need to find out the heating demand in the local communities so that we can displace the natural gas for the biogas heating system. So we're looking to one of the industrial agricultural operation is the greenhouses. Greenhouses requires the heating as well requires the CO2 enrichment to elevate the CO2 concentration in the greenhouse to stimulate the greenhouse operations. Also, another industrial scale agricultural operation is the mushroom housing operation, in which again the heating is required as well as the growth substrate made from the compost. As well, CO2 released from the mushroom growing need to be removed. This will be contrary to the CO2 need to be added into the greenhouse. So we proposed such an eco-industrial agricultural system in which a dairy farm will produce animal waste, and this waste will be digested in the anaerobic digestion system together with the food waste. Then the biogas will be used or burned for the heating demand of the dairy farm, greenhouse, and also the mushroom house. While the biogenic CO2 separated from the biogas can be used for the greenhouse CO2 enrichment, while this digestate will be used to prepare the substrate for the mushroom house or made into the compost as the organic fertilizer for the greenhouse operation. Surplus the digestate can be land spreaded for the crop growing, while the crop residuals can be used to make the substrate for the mushroom operation, while the CO2 released from the mushroom operation can be packed into the greenhouse for the CO2 enrichment. By doing this integration, we should be able to reduce the natural gas consumption for the heating, for the CO2 enrichment, as well as the materials for the substrate for the mushroom, as well as the chemical fertilizers for greenhouse operation. Again, we quantified per dry ton of the animal waste, how much of the CO2 reduction can be achieved. So in the base case, we presented conventional operation in which the animal waste will be land spreaded. You can see it will release a substantial amount of the CO2. The anaerobic digestion of the waste to produce renewable natural gas or for the combined heat power generation or the heating operation will result in negative CO2 emission, while the integration of the greenhouse operation with the AV reactor as well as the mushroom operation and so on will achieve a substantial negative emissions of the greenhouse gases. So this is the best scenario. We also can see for the co-digestion of the cattle manure, poultry manure, and the cattle manure with the food waste, and the cattle manure and the crop residuals, we can have a similar kind of the performance in terms of the CO2 reduction per dry ton of the biomass. In terms of the cost, we also quantify the cost per ton of the dry animal waste managed. Again, these 80 reactors for the renewable natural gas combined heat power and then heating operation will cost about $150 to $200 per dry ton of the animal waste managed, while the integrated systems will reduce the cost to about $50 or below. Again, similar patterns can be observed for different co-digestion operations. This shows the GHG reduction potential per dry ton of animal waste versus the cost per ton of CO2 reduced from different operations. Again, for the 80 reactor operations for different applications, we can see per ton of CO2 reduced, it will cost about $200 to $800. Also, this CO2 reduction potential is about 300 to 800 kilogram per dry ton of the biomass. By integration of the AD system with different industrial agricultural operations, we can see we can increase the CO2 reduction potential per dry ton of the biomass, as well as reduce the cost per ton of the CO2 sequestrated. Okay, so now the cost of this operation is well below the carbon tax currently imposed in the British Columbia, which is $50 per ton. So this makes this integrated system a very, very potential and promising operation. So our recommendation is we need to integrate livestock-based AD systems with the other industrial agricultural operations, like the greenhouse, mushroom house, and then field crops and the food waste, in order to maximize the GHG reduction potential and reduce the operating costs. This is the result I want to report. Although our analysis is a case study for the province of British Columbia, but the same approach and the same methodologies can be applied to other countries and the other region to maximize the GHG reduction potential of biomass residuals. For those of you interested in my presentation, you can look into more detailed results from those 4 publications. Thank you for your attention.
Thanks for the presentation from Xiaotao. And yeah, so Xiaotao is here. Any question from our audience for biomass utilization? Hi, Tony. Just a very quick question from my side. You talk about optimal use. You only show the results. I'm just wondering, like, how you do like modeling, like you do like linear programming for the different pathways, or what do you do?
Well, in our case, we just do some discrete analysis. So basically, we just analyze different pathways, and then we compare them to see which pathway give you the higher reduction potential. So
Okay.
really, there is no optimization strategy applied in this case. Just the
Scenario analysis.
Yeah,
Scenario
exactly.
analysis.
Scenario analysis.
Okay, good to know. Any question from our audience? Just one more question for your case, like what's the data source for like different pathways? Like
Well, we have been doing a lot of the bioenergy research here. So we have some in-house data, also the data from the literature for the biomass availability or the market kind of demand potential. We look into the statistics data from the kind of the different government agencies and so on.
Okay, good.
Yeah. For the life cycle analysis, we use the database from like the GRID or the Canadian LCA database or the CIMA-Pro, that is the European database. But then we prefer to use the database directly relevant to the local operation. But if not available, we supplement with the data from the other regions for the analysis. Yeah.
Okay, cool. Thanks for answering.